Hello, I'm Cody Tillery with Horizon Systems, and today I'm going to be talking about our innovation in negative airlift systems. Preventing harmful pathogens in pet foods and treats has been a focus for food and ingredient manufacturers for a number of years, and all food processes are not exempt from the risk of product contamination. Utilizing hazard and risk analysis to determine where to focus your sanitation efforts within each facility requires an evaluation of systems, components, and facility designs so they work together to combat contamination. Even though the risk is present in all facilities, determining what risks are appropriate for your facility becomes an individual process and company decision. Horizon Systems engineers and manufactures innovative, risk-appropriate, and process-safe material handling and pneumatic conveying solutions. Our emphasis on food safety in the pet food industry has led us to incorporate sanitary design principles into the engineering and manufacturing of our systems and components. We will share several of these innovations today and illustrate how they are incorporated in the design of our negative airlift system. In dry pet food manufacturing, the extrusion cooking process has become generally recognized as a bacterial reduction or kill step. Production lines for dry extruded pet food convey wet product from the extruder discharge to the inlet of the dryer. This conveying process is normally done via a negative airlift system that pulls product directly from the extruder die and cutter assembly. These systems use a large volume of air for conveying to minimize contact between individual pieces of product and promote a small amount of surface drying so that the product doesn't stick to itself or the interior of the conveying equipment. The product is typically still flashing off a large volume of moisture at the extruder die, so the airstream in these systems is typically warm, 150 degrees Fahrenheit or higher, and saturated with moisture. A poorly designed negative airlift system can present a significant potential for product recontamination while conveying the product to the dryer. Microbial contamination within the conveying system can be significant since the process conditions inside the system can support the growth of many microorganisms. The best way to minimize the risk of post-extruder contamination is to review the design of the facility, as well as the design of your system and each individual piece of equipment. Equipment design and facility zoning are part of an overall sanitation program needed to address the risk within your process. First, you must assess what your risks are within your process and then determine how active, passive, and preventative sanitation can be used to minimize the risk. Active sanitation is the process used to clean your system. Active sanitation has 3 steps: clean, sanitize, and verify. Using wet and dry cleaning methods like hot water or dry ice along with ozone or liquid sanitizer will allow you to clean and sanitize most of your high-risk areas. Verifying cleaning results visually or through a culture test will be difficult if you have convey lines and equipment that are not designed for easy access and inspection. Passive sanitation involves both equipment design and facility zoning. Designing access for active sanitation, eliminating hot spots, dead areas, and using the proper finishes are critical engineering design elements for equipment. Clearly planned zones based on product risk, traffic management, and air and water management are all important for sanitary facility zoning. Preventative sanitation is the creation and execution of the overall plan. It includes an ongoing facility hazard analysis, documented procedures, ingredient tracking and allergen management, and employee training to properly execute a full sanitation program. A well-designed negative airlift system will minimize the potential for product recontamination. An optimal design includes the following main components. The first is air supply and treatment. Second is extruder takeaway hood. 3 is convey piping. 4 is air and product separator. 5 is discharge rotary valve. And the 6th is the air exhaust fan and blocking valve. The first component is air supply and treatment. Passive sanitation includes designing the proper facility air balance between process zones and air supply for each system, including the negative airlift system. Drawing or supplying contaminated air into the production stream is a risk since the air in the system has full contact with the product. By slightly pressurizing the extruder hood, air leakage becomes less of a concern because air is forced from inside the system out rather than drawing air from outside the system in. The pressurized air supply and treatment system should include a pressure fan as part of a filtration system efficient enough to remove microbes including airborne salmonella. The air supply system may also provide the air conditions needed for a sanitizing step when the system is down and clean. Heat or ozone generation systems have been commonly used for active offline sanitizing of the interior surfaces of the conveying system. The second component is the extruder takeaway hood. The hood encloses the extruder die and cutter assembly when running. It directs airflow across the die so product is introduced properly into the pickup airstream. There are critical areas that should be considered when designing the hood. These include the airflow distribution across the die area, sealing around the cutter drive shaft, sealing of the hood to the extruder die and overall accessibility of the extruder components for die changes, cleaning and maintenance. Design features include the ability to divert air away from the pickup to allow product to fall to the reject system or floor during extruder startup and upset conditions. Other design features that can be included with the extruder takeaway hood include product sampling systems, instrumentation for monitoring pressure fluctuations of the air conveying system at the hood, and instrumentation for monitoring sanitizing cycles. The third component is convey piping and couplings. Product convey line or piping is an important part of the conveying system. It can have more surface area in contact with the product than any other piece of equipment in the system. The piping system includes straight sections of pipe, elbows for changes in direction, and couplings for joining sections of pipe and elbows. Passive design requirements suggest straight piping and elbow should be chosen with a smooth interior finish that minimizes seams and surfaces that will allow fines to be trapped. Elbows should be chosen with the shortest radius that can be bent without causing ripples on the interior. All elbows cause some turbulence, which allows fines to build up inside the elbows where product does not scrub the interior surface. Active provision should be made to clean the elbows via dismantling and direct access or some other CIP or clean-in-place method such as line pigs or dry ice. Couplings provide sealing at joints and alignment of piping components. Couplings should be chosen that provide a minimum ledge at the joint. It is very important that the coupling is airtight so that contaminants are not drawn into the system at the conveying joints. It is important to remember that couplings are not intended to provide structural support of piping components. Proper support of the piping system is critical to its long-term performance and structural integrity. The fourth component is the air product separator. This removes product from the conveying airstream so that it can be discharged from the system. Traditionally, this has been accomplished via a cyclone separator. Cyclones present access challenges that make them hard to clean. Over time, fines will build up on any interior surface that is not scrubbed by product. This buildup occurs mostly in the upper part of the body of the unit. Newer designs of product-to-air separators, such as Horizon Systems' new Clean Horizontal Product Separator, provide better access for cleaning and sanitizing the interior of the unit. These designs are also more compact, allowing flexibility in the system layout, which allows equipment to remain inside the building, eliminating exposure to the elements outside the building. The fifth component is the discharge rotary valve. This valve is mounted to the bottom of the material-to-air separator. It allows product to exit the system to the dryer while providing a seal to minimize air being pulled into the system through the discharge point. There are several areas inside a rotary valve where fines can build up. Fines can build up in the base of rotor pockets, shaft sill areas, and housing throats. These areas cannot be easily accessed in a standard rotary valve. The answer is a quick or easy clean rotary valve design, which allows the valve to be disassembled for cleaning. Valve designs should be chosen based upon ease of disassembly, durability, and safety, as well as sanitation. The final component is the air exhaust fan and blocking valve. This provides a static suction pressure to convey the product through the system. It also exhausts air from the air product separator. The air from the fan is typically exhausted outside the facility since it is high in temperature and saturated with moisture. The connection of the system exhaust to the plant discharge presents a risk that contaminated air can be pulled back into the system when the system is not operating. A system discharge blocking valve should be used to seal off the exhaust when the system is not in operation. The blocking valve, in addition to proper overall facility zoning and air management, will help keep contaminants from entering the system. Besides components, there are several facility design parameters that should be considered when installing a new system or modifying an existing one. These include air balance between plant hygienic zones, cleaning methods, sanitizing methods, and process flexibility needed for different products. The negative airlift can have an effect on and be affected by air balance within plant zones. Typical airlift systems move 2,000 to 8,000 CFM. If this flow is not accounted for in the plant air balance, flow from low hygiene to high hygiene zones can present a food safety risk. Inadequate makeup air systems can also starve the system for airflow and cause product conveying issues. Active sanitation should specify cleaning methods and chemicals that are compatible with equipment materials of construction. If chemicals are used that are not compatible with equipment components, equipment will fail prematurely and contamination from damaged product contact surfaces can occur. Equipment designs must also be compatible with sanitizing methods. As with sanitizing chemicals, equipment components should be compatible with additional sanitizing methods such as heat and ozone. Active and passive sanitation within a negative airlift system or any process system will not work effectively without a preventative sanitation plan. Employees must be trained to execute the plan and be aware of the procedures and safety measures required to be successful. Determining the appropriate risk, documenting procedures, tracking ingredients, and training will help you protect your consumers, employees, and brand. In conclusion, in order to minimize contamination risk in a negative airlift system, all aspects of a production process must be examined. The goal is to determine the best overall solution for your production site, and that starts with a hazard analysis and risk assessment of the proposed new system or retrofit. Preventative sanitation not only starts the risk conversation, it is also responsible for educating employees, documenting procedures, and tracking performance. Passive sanitation principles in facility, system, and equipment design minimize risk to production and enhance the effectiveness of an active sanitation program. Equipment that is easy to clean and inspect is equipment that gets cleaned properly. Eliminating or reducing dead areas, using the proper finishes, and reducing ledges and bins and convey lines will all contribute to reducing risk. Understanding facility airflow patterns, equipment air usage, and traffic patterns are just as important as the design of the component. And finally, determining the best active sanitation program requires understanding where the process risks exist and having procedures in place for employees to clean, sanitize, and verify your process is safe. Thank you for your time today. We hope you enjoyed our presentation. To read our entire white paper, please visit sales.horizonsystemsinc.com. For more information, you can also visit our website at www.horizonsystemsinc.com.